According to the National Electrical Code Section 250.148a, equipment grounding conductors shall be run with the circuit conductors and shall terminate in the equipment grounding bus in the panel board. This requirement means that the branch circuit ground should land on the ground bus in the panel board where the circuit originates. The ground bus in the panel board is the primary point of reference for grounding all equipment and circuits in the system. Landing branch circuit grounds directly on this bus ensures a reliable and low impedance path to ground. The National Electrical Code specifically requires grounds to terminate in the equipment grounding bus in the panel board, not in other electrical equipment. Landing grounds on a ground bus outside of the panel board can create ground loops which can compromise the effectiveness of the grounding system. It is best to not allow branch circuits to pass through panels on their way to another panel. Ground branch circuits by landing their equipment grounding conductors in the ground bus in the panel board where they originate. Additional reference: the National Electrical Code Section 250.146 states that equipment grounding conductors shall be connected to the equipment grounding conductor terminal on the equipment. Therefore, to reiterate, branch circuit grounding conductors must terminate on the equipment grounding bus bar within the panel board where the branch circuit originates, and should not pass through intermediate panels on their way to another final destination panel board. This is for several important reasons. Firstly, safety is paramount. A direct connection to the panel board's grounding bus ensures the lowest possible impedance path for fault current to return to the source. This low impedance is crucial for quickly tripping over current protection devices such as circuit breakers or fuses, minimizing the duration of any fault and reducing the risk of electrical shock or fire. Secondly, compliance with the National Electrical Code, or NEC, is not just a good practice, it is a legal requirement in most jurisdictions. The NEC is very specific about grounding requirements, and Section 250.148 clearly states that equipment grounding conductors must terminate in the equipment grounding bus within the panel board. Deviation from this requirement is a code violation and can result in failed inspections or potential safety hazards. Thirdly, ground loops can create significant problems in electrical systems. A ground loop occurs when there are multiple paths to ground, creating a circulating current within the grounding system. This circulating current can cause a variety of issues, including noise in sensitive electronic equipment, inaccurate readings from instrumentation, and even the potential for shock hazards. By ensuring that each branch circuit has only one path to ground, which is directly to the panel board's grounding bus, we minimize the risk of creating ground loops. Consider a scenario where a branch circuit originates in panel A, passes through panel B, and then supplies power to equipment at a remote location. If the grounding conductor for this branch circuit were to land on the grounding bus in panel B instead of panel A ground loop could be created. The current could flow from the equipment back to panel B's grounding bus, and then back to panel A's grounding bus through the building's grounding system. This circulating current can be avoided by ensuring that the grounding conductor lands directly on the grounding bus in panel A, where the circuit originates. Furthermore, the practice of running branch circuits through intermediate panels can also create confusion during troubleshooting or maintenance. It can be difficult to trace the path of a circuit if it passes through multiple panels, especially in complex electrical systems. By adhering to the principle of originating the branch circuit and its associated grounding conductor in the same panel board, we simplify the system and make it easier to maintain and troubleshoot. In addition to the NEC requirements and the avoidance of ground loops, there are also practical considerations that support the practice of landing branch circuit grounds on the originating panel board's ground bus. Firstly, this practice ensures a consistent and organized approach to grounding. When all branch circuits within a panel board have their grounding conductors terminated on the same grounding bus, it creates a clear and easily understandable grounding scheme. This consistency is particularly important in large or complex electrical installations where multiple electricians or technicians may be working on the system over time. Secondly, landing branch circuit grounds on the originating panel board's ground bus simplifies testing and verification of the grounding system. During commissioning or routine maintenance, it is essential to verify that the grounding system is functioning correctly. By having all grounding conductors terminated in a central location, it becomes much easier to perform continuity tests and impedance measurements to ensure that the grounding system is providing a low impedance path to ground. Thirdly, the practice of landing branch circuit grounds and the originating panel board's ground bus promotes a more robust and reliable grounding system. When grounding conductors are properly sized and installed, they provide a solid and dependable connection to ground. This reliable connection is essential for ensuring the safety of personnel and equipment, as well as the proper functioning of electrical and electronic systems. Now let's delve a little deeper into some specific aspects of grounding and bonding in electrical systems. Grounding and bonding are often used interchangeably, but they are actually two distinct concepts. Grounding refers to connecting an electrical system or equipment to the earth, while bonding refers to connecting various metallic parts of an electrical system together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety and are required by the National Electrical Code. The equipment grounding conductor, often referred to as the EGC, plays a critical role in both grounding and bonding. The EGC is the conductor that connects the non-current carrying metal parts of electrical equipment to the grounding bus in the panel board. This conductor provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly trip and clear the fault. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. The National Electrical Code provides tables that specify the minimum size of the EGC based on the ampere rating of the circuit breaker or fuse. It is important to select the correct size EGC to ensure that it can safely carry the fault current and provide a low impedance path to ground. In addition to the equipment grounding conductor, there is also the concept of the grounded conductor, often referred to as the neutral conductor. The grounded conductor is the conductor that is intentionally grounded at the service entrance. In most electrical systems, the grounded conductor is connected to the grounding electrode conductor, which connects the electrical system to the earth. The purpose of grounding the neutral conductor is to provide a stable reference point for voltage and to limit the voltage to ground. This helps to prevent overvoltages and protect equipment from damage. It is important to note that the grounded conductor and the equipment grounding conductor are two separate conductors with different functions. The grounded conductor carries current under normal operating conditions, while the equipment grounding conductor only carries current during a fault. The two conductors should never be connected together except at the service entrance or at separately derived systems. Another important aspect of grounding is the concept of bonding. Bonding refers to connecting various metallic parts of an electrical system together to create a low impedance path for fault current. This includes bonding together metal conduits, metal enclosures, metal equipment frames, and other metallic parts. The purpose of bonding is to ensure that all metallic parts are at the same potential, which helps to prevent shock hazards. When a fault occurs, the fault current will flow through the bonding conductors, creating a voltage drop. If the bonding conductors are not properly sized or installed, the voltage drop can be significant, which can create a shock hazard. Therefore, it is important to select the correct size bonding conductors and to ensure that they are properly installed. The National Electrical Code provides specific requirements for bonding, including the size and type of bonding conductors, as well as the methods for connecting them. In addition to the general requirements for grounding and bonding, there are also specific requirements for certain types of equipment and systems. For example, there are specific requirements for grounding and bonding in healthcare facilities, industrial facilities, and hazardous locations. These specific requirements are designed to address the unique hazards and challenges associated with these types of facilities. It is important to be familiar with these specific requirements when working on electrical systems in these types of facilities. Let's consider a few examples to illustrate the importance of proper grounding and bonding. Firstly, consider a scenario where a metal conduit is not properly bonded to a metal enclosure. If a fault occurs inside the enclosure, the fault current will flow through the conduit to ground. However, if the conduit is not properly bonded to the enclosure, there may be a high impedance connection between the two. This high impedance connection will create a voltage drop, which can create a shock hazard. If someone touches the enclosure, they could receive an electrical shock. Secondly, consider a scenario where an equipment grounding conductor is not properly sized. If a fault occurs in the equipment, the fault current will flow through the equipment grounding conductor to ground. However, if the equipment grounding conductor is not properly sized, it may not be able to safely carry the fault current. This can cause the equipment grounding conductor to overheat and potentially melt, which can create a fire hazard. Thirdly, consider a scenario where a ground loop exists in an electrical system. If a ground loop exists, circulating currents can flow through the grounding system. These circulating currents can cause noise in sensitive electronic equipment, which can interfere with its proper operation. In addition, the circulating currents can also create a voltage drop, which can create a shock hazard. These examples illustrate the importance of proper grounding and bonding in electrical systems. Proper grounding and bonding are essential for electrical safety and are required by the National Electrical Code. By following the requirements of the NEC and using good electrical practices, we can ensure that electrical systems are safe and reliable. Now, to further clarify the National Electrical Code requirements related to equipment grounding conductors, let's consider specific sections and their interpretations. As previously mentioned, National Electrical Code Section 250.148 is a cornerstone for understanding where equipment grounding conductors must terminate. This section mandates that equipment grounding conductors be run with the circuit conductors and terminate in the equipment grounding bus within the panel board. The key here is the phrase equipment grounding bus in the panel board. This is not a vague suggestion, but a firm requirement. It means that the physical connection of the grounding conductor must be made to the designated grounding bus bar within the panel board that serves the circuit. To further expand on this, let's consider the implications of the phrase run with the circuit conductors. This means that the equipment grounding conductor must follow the same physical path as the circuit conductors, which are the hot and neutral wires. This is important for minimizing impedance and ensuring that the grounding conductor can effectively carry fault current back to the source. When the equipment grounding conductor is run separately from the circuit conductors, it can create a higher impedance path, which can reduce the effectiveness of the grounding system. Another important section to consider is National Electrical Code Section 250.45, which discusses the requirements for effective grounding paths. This section states that the grounding path must be permanent and continuous and have the capacity to conduct safely any fault current likely to be imposed on it. This reinforces the importance of using properly sized grounding conductors and making sure that all connections are tight and secure. In addition to these general requirements, there are also specific requirements for grounding different types of equipment. For example, National Electrical Code Section 250.110 covers the grounding of equipment fastened in place or connected by permanent wiring methods. This section requires that all non-current carrying metal parts of this equipment be grounded. This includes things like metal enclosures, motor frames, and other metallic parts that could become energized in the event of a fault. To comply with National Electrical Code Section 250.110, equipment grounding conductor must be run from the equipment back to the grounding bus in the panel board. This can be accomplished by using a wire-type equipment grounding conductor, or by using the metal conduit or cable armor as the equipment grounding conductor, provided that it meets certain requirements. In some cases, it may be necessary to use a combination of wire-type equipment grounding conductors and metal conduit or cable armor to provide an effective grounding path. For example, if the metal conduit is not continuous, it may be necessary to supplement it with a wire-type equipment grounding conductor to ensure that there is a continuous grounding path back to the panel board. Furthermore, National Electrical Code Section 250.130 covers the grounding of cord and plug connected equipment. This section requires that all cord and plug connected equipment that is likely to become energized be grounded. This can be accomplished by using a 3-wire cord and plug, with the third wire being the equipment grounding conductor. The equipment grounding conductor must be connected to the grounding pin on the plug, and the grounding pin must be connected to the grounding terminal on the receptacle. When cord and plug connected equipment is properly grounded, it provides a safe and effective way to protect against electrical shock. If a fault occurs in the equipment, the fault current will flow through the equipment grounding conductor back to the panel board, causing the circuit breaker to trip and to energize the circuit. This helps to prevent electrical shock and protect equipment from damage. In summary, the National Electrical Code provides comprehensive requirements for grounding and bonding in electrical systems. These requirements are designed to ensure the safety of people and equipment and to provide a reliable and effective grounding system. By following the requirements of the National Electrical Code and using good electrical practices, we can minimize the risk of electrical shock and fire and ensure that electrical systems are safe and reliable. Remember that local amendments to the National Electrical Code might exist, and it's important to check with your local authority having jurisdiction to ensure compliance with all applicable regulations. Proper grounding and bonding are not just about meeting code requirements, they are about creating a safe and reliable electrical system that protects people and property. Understanding the principles and practices of grounding and bonding is essential for anyone working with electrical systems.